Did you know that ejectors are the simplest, most reliable, and trouble-free of vacuum-producing equipment? They provide the largest capacity of all vacuum pumps and are a static piece of equipment with no moving parts. While ejectors may be one of the simplest, most reliable, and in some cases, most critical pieces of equipment in your process, they may also be the piece of equipment that is the least understood by those in the field. Knowing the basic components and operating fundamentals of a well-performing ejector will allow you to effectively apply ejectors to your process. In this video, we are going to provide a foundation for understanding ejectors. We'll discuss critical steam ejectors, their components, and the principles of operation. Here we have an ejector made of glass, which we will use in order to illustrate the distinguishing characteristics that define a well-performing critical ejector. There are four major components to an ejector: the motive nozzle, motive chest, suction chamber, and diffuser. An ejector works by converting the pressure energy of the motive fluid, otherwise known as potential energy, to velocity energy or kinetic energy. This is accomplished by the adiabatic expansion from the motive fluid supply pressure to the suction load pressure as motive fluid flows through a converging-diverging nozzle, as you can see happening here in the glass ejector. Now we will move on to discuss the four major components in more detail. The first component is the motive chest. This is where the motive fluid enters the ejector. In our case, and most cases for Graham equipment, the motive fluid is steam. However, it can be any fluid that is at a higher pressure than the ejector is trying to compress to. The second component is the motive nozzle. Once the motive steam enters the motive chest, it expands adiabatically across the converging-diverging motive nozzle, converting pressure to velocity. The pressure differential across the motive nozzle accelerates the motive fluid as it rushes to the lower pressure region of the suction chamber. A well-designed converging-diverging nozzle efficiently converts high-pressure motive to a high-velocity stream, leaving the divergent section of the nozzle. The motive gas actually expands to a pressure slightly less than the suction load pressure. That creates a localized low-pressure region, which draws in the suction load vapor. The design and location of the motive nozzle is set by the manufacturer for your specific operating conditions and plays an essential part in ejector performance. Housing the motive nozzle is the third component we are going to discuss, the suction chamber. This is the mechanical connection between the nozzle and the rest of the ejector. The high-velocity motive stream mixes and entrains the processed gases in the suction chamber. Momentum is transferred from the high-velocity motive stream to the suction load gases, accelerating the suction load gases and, consequently, decelerating the motive gas to a new mixture velocity. The fourth and last of the major components is the diffuser. The mixed gas stream enters the diffuser, where velocity is converted back to pressure, and is where the work of the compression occurs. The diffuser consists of three sections: the inlet converging section, throat section with constant area, and outlet diverging section. In the inlet converging section, the mixture velocity is decreased and pressure is increased as the cross-sectional area is reduced. Remember that for gas flow at supersonic velocity, velocity and pressure variations due to the change in cross-sectional flow area are the opposite of what one would expect with subsonic fluid flow. The diffuser throat is sized to achieve an optimal transonic shock system. The transition from supersonic to subsonic flow across the shock system produces a dramatic increase in pressure. Slightly more than half of the total compression achieved in an ejector is obtained in this section. The static pressure, temperature, and density increase across the shock system, whereas velocity decreases. The pressure is increased further in the outlet diverging section of the diffuser, where the subsonic mixture is reduced as cross-sectional area increases from the throat diameter to the discharge diameter. Slightly less than half of the total compression achieved in an ejector is obtained in the outlet diffuser section through simple deceleration of the subsonic flow. To further expand on the principles of operation, here we have a two-dimensional hydraulic simulation of the flow through an ejector, which can be visualized on what we refer to as a wavetable. The height of the water in the wavetable is analogous to the pressure in an ejector. The motive nozzle expands the high-pressure motive fluid down to a pressure lower than the designed suction pressure. As the high-velocity motive flow leaves the nozzle, it comes in contact with the suction fluid and begins to mix with it, entraining it as you can see here. The pressure will slightly increase through this section, causing the water level on the wavetable to rise. Through the throat, there is a step change in pressure, temperature, and velocity across the shock wave. Pressure and temperature increase while velocity drops below sonic, which can be seen here as a sharp increase in height. In many cases, one can feel the temperature difference across the shock wave. More than 50% of the ejector's compression is done across this shock wave, which is why it is so important to the ejector's operation. The outlet diffuser is diverging and contains subsonic flow. This continues to slow the velocity of the flow by increasing cross-sectional area and increases the pressure up to the final discharge pressure. These same principles are seen in a well-performing ejector. Through the glass diffuser, you can visualize the shock wave as the rapid increase in pressure briefly condenses droplets of water. This is the same phenomenon as the sharp increase in water height that was shown on the wavetable. We hope that you now understand the basic components and operating fundamentals of a well-performing ejector. Keep in mind that in order for an ejector to work properly, it has to be correctly sized for your unique operating conditions. Please do not hesitate to contact Graham directly concerning technical and sizing questions.